So I welcome all the KPM members, students, and other invitees to this online lecture series. So as you know, we have been conducting these lectures on a variety of topics for the benefit of our students and teachers, mainly with the idea of introducing them to developments in various topics that they might not have studied in detail earlier. So subject is growing in leaps and bounds, and we have to learn about them and help, so that it helps us in teaching also. So with that point of view in mind, we have contacted several faculty members from universities, colleges, and institutes to give informal talks at the degree level or PG level so that our teachers can benefit. And we have also conducted some of the talks in Kannada also, with the view of encouraging the usage of Kannada in higher education for the benefit of students and teachers and ease of communication. So ultimately, if Atmanirbharta has to take place, finally we have to switch over. But when that happens, we don't know. But let us make an attempt in introducing our regional languages into higher education, which other institutions, other educational policies also suggest, but they have not taken a very serious measures in that direction. So today's speaker, we have a distinguished speaker from ICTS, who is a native of Bangalore, and he's going to talk about physics of life, a new subject. He's involved in evolving a very innovative program at ICTS in this particular field. So he will tell us more about that. So before I request him to speak for maybe about 50 minutes or so, and then answer questions for about 10 minutes, I request our Joint Secretary, Dr. Rudraswamy, to briefly introduce the speaker.
Yes,
over
sir.
to Dr. Rudraswamy.
Thank you, sir. Thank you for the opportunity, sir. It is indeed a great honor and immense pleasure to introduce and welcome an eminent speaker, Professor Dr. Vijaykumar Krishnamurthy. Dr. Vijaykumar Krishnamurthy is presently serving as an associate professor at the International Center for Theoretical Science of the Tata Institute of Fundamental Research. He obtained his PhD degree in theoretical physics from Indian Institute of Science, Bengaluru. He was postdoctoral fellow at Yale University, USA, and Max Planck Institute at Dresden University, Germany. His research areas of interest are interface of theoretical physics and biology, and fascinated by morphogenetic processes at the level of cells and tissues. He has been part of developing a new PhD program in TIFR called Physics of Life, which aims to attract students with backgrounds in physics, mathematics, and engineering to work on challenging problems posed by living systems. With this brief introduction, I cordially invite an eminent speaker, Professor Vijaykumar Krishnamurthy, to deliver a talk on an important topic, physics of life. Over you to sir. Thank you very much.
Thank you very much. Thanks everyone for turning up on a Sunday morning, and thanks to the Karnataka Physics Association for inviting me to give this talk. I hope my cursor is visible and the laser pointer is also visible.
Yeah.
Thank you. Thanks a lot. I'll go ahead and I will start very slowly, and I'll give you a broad overview of this area. And here's an outline. I first want to address something that might be bothering all of us. Is this topic even physics? And I'll show you that there is a very nice way to think about living systems as condensed materials, just like solids, liquids, and gases that we learn. But I'll point out that living systems operate far from thermodynamic equilibrium. So this is different from the kind of condensed matter that we usually learn. I'll argue that living systems self-organize, that is, they make themselves. And one of the more recent physics developments, which potentially has the ability to explain this self-organization, is this area of active matter. And I'll show you some examples where this framework is capable of explaining biological self-organization. If time permits, I'll briefly touch upon my own work in the last topic on mechanochemical patterns. I'll conclude with a summary and I'll point to some suggestions for further reading. So the first question is, of course, is this physics? And maybe even before that, what is life? This is a fantastic book by none other than Erwin Schrödinger, the same Schrödinger of the Schrödinger equation that we learn in quantum mechanics. And so after he had built the foundations of quantum mechanics, he wrote this wonderful book in the 1940s, where, this was not a reflection about what happened to his life or anything like that. Given the serious scientist that Schrödinger was, he really was wondering about the physical aspects of the cell. So in particular, the questions that he addresses in this book are the following. The very main question that he puts out very earlier on in the book is the following. He asks, how can the events in space and time, which take place within the spatial boundary of a living organism, be accounted for by physics and chemistry? In other words, you want to understand the processes that happen within an organism, and how is it the laws of physics and chemistry give rise to those kinds of processes. He goes on to explain many of these processes. And in particular, he asks, what do you mean by saying a piece of matter is alive? And so he defines it, for instance, by saying that when it goes on doing something, moving, exchanging, much longer than typically would be expected of an inanimate piece of matter. That's a rough working definition of what is meant to be alive. We all know the following. We all learn this in undergraduate physics, that if you take an isolated system and keep it far away, eventually it will reach thermodynamic equilibrium. It will do so even if it's in contact with a heat reservoir. However, living systems, including us, avoid this rapid decay into the inert state of thermodynamic equilibrium, and that's what makes them really fascinating and enigmatic. Now, how do they do that? Well, the obvious answer is eating, drinking, breathing, in the case of plants, assimilating. And the technical term is, of course, metabolism, the process by which we take in energy and matter from the surroundings and use that to avoid decaying into thermodynamic equilibrium. He also argues that what is it that is actually contained in our food? Typically, we think it's energy, but he shows you with very clever arguments that it's actually negative entropy. We all learn entropy increases without bound. The second law says that the entropy will never decrease. Living systems, on the other hand, avoid this decay by feeding upon negative entropy. It's a wonderful, remarkable book that everybody in science must read. It gives you a flavor for how to think about living systems as essentially emanating from the laws of physics. This continues. There's a wonderful Russian book. Many of us used to buy these on footpaths in Avenue Road in Bangalore. This is how I got this book too. Fundamentals of Physics by Ivanov. A wonderful book which introduces physics from very deep principles. And towards the end of the book, in the concluding remarks, he highlights a bunch of points. The yellow highlighted sentences I've put on the right. He says, well, let's look at the main trends that are there in the development of natural sciences, and in particular physics. There are three main areas. So there's elementary particle physics, there's astrophysics and cosmology, and surprisingly, he says molecular biology. And molecular biology he considers as a part of physics. And if you just look at it cursorily, you see that, the elementary particle physics looks at the study of the smallest. Cosmology and astrophysics, you look at the study of the largest. And molecular biology is really the study of the most complicated states of matter. So there's a new angle. Rather than thinking about big and small, there's also a complexity, which is really what distinguishes living systems from non-living systems. But is this physics? Is this area physics? Is this something worth teaching and developing at the undergraduate level, at the master's level, at the PhD level? Is this something that we should teach? Is this where physics will go? Many of us who work in this area, we don't need the recognition that this is physics. Yes, of course, it is physics, without a doubt. But then it also helps to have institutional and formal support for this area being called physics. Here's something that happened a couple of years ago. In the US, the National Academies of Sciences, Engineering, and Medicine, together called the National Academies, they do a survey of the state of physics every 10 years. So the idea is that every 10 years, you get a bunch of people together, some expert committees, and you ask them, where is physics going? This is useful because the government has to make decisions on, where to invest funding, what teaching programs to develop, which research areas to sponsor. So there's a practical aspect to this problem as well. Physics, as we all know, is very large. So therefore, typically, this is broken down into many, many sub areas. Standard areas like astronomy, astrophysics, atomic, molecular, optical physics, elementary particle physics, condensed matter physics, and so on. For the first time in 2022, biological physics, or the physics of living systems, stood alongside these traditional fields of physics as a genuine part of physics. For many of us who are working in this area, sort of a ill-defined area where people have existential questions about how is this physics? Are you a physicist? This report gave us tremendous reason to celebrate, because this said, yes, this is indeed physics. So there's a committee, and the committee was tasked and with the following agenda: take a broad view of the field, think about the connections of the field to different other fields in physics. What are the challenges that the field faces, and what is it that we can do to realize the field's potential? So there's a report that came up, Physics of Life. I've put the link to the report at the end of the slide. Please take a look at this. It's a long 300-page report. I'll give you a summary of that in the next slide. But the more important thing is the kind of recommendations it makes, saying that biological physics is a genuine branch of physics. It must be part of the undergraduate curriculum. It must be part of the master's curriculum. It must be developed as a strong research area. A significant amount of new breakthroughs will happen in this area. And so therefore, this is a recommendation that the committee makes to the US government. The report starts out by asking some very nice questions. The essential question is essentially the following. They ask, what are the physical principles that enable the remarkable phenomena of life? Notice the emphasis is on the principles, the physical principles. The report concludes, this is a summary, that biological physics now has emerged as a fully developed field of physics alongside the more traditional branches that we learn at the undergraduate and master's level. Now, we were all fascinated. I, along with colleagues at Tata Institute, TIFR, we were trying to develop this area. We are building this area. So we thought it would be most appropriate if we get somebody from the committee that wrote this report to tell us more. We were lucky. We got Professor William Bialek, who was the chair of the committee that drafted this report. And we organized a colloquium, aptly titled Physics of Life. This was an online colloquium. I have given the link to the colloquium in the QR code. If you scan the QR code, you'll be able to reach the YouTube lecture. Professor Bialek argues very, very coherently that what is the history? What is the history? What is the history of this field? What are the kinds of challenges it faces? And what are the kinds of difficulties that are there? Am I audible?
Sure, please go ahead.
Thank you. What are the kinds of challenges it faces? And what are the kinds of teaching resources, books, programs that one should develop? So this lecture makes a really good case. My hope is that many of our meta institutions like academies and associations will actually take up this challenge. Remember, we're trying to describe living systems as physical systems. Not to say that physics is not being useful to biology in the past. Of course it does. In particular, we all recognize traditional biophysics as a venue where physics provides tools for biology, most prominent being microscopes. It could be optical microscopes, fluorescence microscopes, or even more sophisticated scanning electron microscopes. But then these things have developed to such a good extent that the physics principles underlie many of the things that we experience in our everyday life. If you go to a hospital, there are examples of MRI scans or PET scans where we use the information obtained from these scans to diagnose disease. But not just that, even fundamental ideas like the structure of the DNA, we understood by looking at X-ray diffraction patterns. So scattering techniques that we had learned somewhere else were applicable to understand the structure of DNA. But remember, the report is not saying that this is biological physics. Of course, there's biophysics. Physics provides tools and technology. The report is arguing that physics and its branches have a new branch called biological physics, in the sense that this starts asking physics questions about living systems and not just providing tools to interrogate living systems. Standard physics questions that we learn in undergraduate classes. What is the radiation spectra of atoms and molecules? How do metals conduct electricity? How does fluid flow happen? How do planets move around? Why does a black hole form, or why is it stable? Or what are the large-scale patterns in the universe? These are the questions. We use a bunch of tools to interrogate these kinds of questions. There are similar questions in the living world. There are questions about how directed transport is achieved in cells. How do cells move, polarize, divide? How do many body dynamics of cells lead to emergent patterns in tissues? How do neurons, which interact with each other very, very strongly, lead to the phenomena of being, say, conscious? How do interspecies interactions lead to the stability of ecosystems? And at a much larger scale, what's the statistical physics of evolution? Remember, the approach is trying to ask questions about the organization, stability, and the response of living systems, exactly like we do in any physical system. So we would write down theory, which includes mathematical models at various levels. We do experiments, which involve quantitative measurements of whatever is possible. But then there is a strong crosstalk between the theory and the experiment. You write a theory, you go check in the experiment. Maybe you do an experiment, you ask what is a theory. So there's this feedback between theory and experiment, which really defines physics, physical processes, be it at the level of atoms and molecules or the entire universe. This approach is what is to be brought into looking at living systems, biological systems. And the report argues that biological physics is an area that takes this approach. So one should ask, is there a theoretical physics of living systems then? Just like there's a theoretical physics of fundamental interactions, of materials, matter, microscopic materials, or astrophysical processes. Surely there are deep philosophical questions that are troubling. Many of these are addressed in this review. This is one of them. There are several such reviews available now. This review argues and shows that there is indeed a genuine theoretical physics of living systems. Here's a bunch of sentences from the abstract. As we all know, theoretical physics searches for simple and universal mathematical descriptions of the natural world. But if you look at typical biology textbooks, it's really an exploration of the complexity and the diversity of life. A significant part of biological textbooks at the high school level involves questions about classification, finding out many factual data. So Bill Bialek argues, for many people, this contrast is prima facie evidence that theory, like in the sense that physicists use the word, is just impossible. For many others, it's a very, very grand challenge. It says, well, we believe physics works at every level, and the physical approach works. It's just that we don't have the right language. We don't have the right physics to describe living systems. So therefore, it's a grand challenge to actually sit down and develop that theoretical physics. I belong to this camp. We believe that there is indeed a physical description of living systems. It's just that we don't have it right now. What I want to show in this talk is a couple of instances where a physicsy description has actually turned out to be very useful for understanding living systems. So this gives hopes that, if you push this further, maybe in a long term, there will be a theoretical physics of living systems. I want to give you a condensed matter view of living systems. This is perhaps a biased perspective because of my training. There could be others who might give you a different perspective, but this is one where I'll show you some examples where it has turned out to be quite useful. Remember, we learned that there are these four fundamental interactions in nature. There's a strong nuclear force, the weak nuclear force, electromagnetism, and gravitation. The strong force holds quarks and nucleons together, while the weak force is responsible for processes like beta decay. Electromagnetism is familiar. We all work and look at equations that charges and currents and electric and magnetic fields. Gravitation is perhaps the most familiar. It comes into action every time we fall down. At the scale of living systems, the most predominant force seems to be electromagnetism, particularly in its statistical manifestations. Remember, matter is charge neutral, so therefore you won't have monopole interactions. You will have higher order interactions like dipoles and quadrupoles and so on. But once you have these fundamental interactions, you need to understand the rules by which motion happens, movement happens. As we all learn in undergraduate physics, they seem to be two large realms. At the size of everyday objects, much larger than atoms, we learn that there's Newton's laws of motion. There's momentum, and the rate of change of momentum is given by the force that's acting on the system. And this applies to larger objects like large molecules, cells, cricket balls, organisms, planets, stars, and galaxies. But when you look at systems at the level of atoms, we know that the rules of the game change. We have to look at not in terms of forces and Newtonian classical concepts, but we have to bring in ideas from quantum mechanics. And in particular, there's the wave function psi, and the Schrodinger equation tells you how the wave function changes in time if you give me the Hamiltonian. The Hamiltonian is where we learn that the interactions of the system are buried in. As we all know, successfully, quantum mechanics explains spectra, chemical reactions, why there are metals and magnets and semiconductors, and so on. Remember, this is the same Erwin Schrodinger whose Schrodinger equation we all learn, the same Schrodinger equation who wrote the first slide that I showed you, what is life? Typically, in undergraduate and master's level, we learn to solve problems at the one body level. Free particle, particle in a potential, and so on. A little bit of a sophistication, we try to, at least formulate the problem for many body systems, but we can't solve them. Some of the most familiar ones that we all learn to solve is the two-body problem in classical mechanics, right? It could be electromagnetism or gravitation, but that's the typical problem that we all learn to solve. However, we also soon realize the n-body problem is not solvable. The same idea that you took for gravitation and wrote down Newton's laws, one can't solve the three-body problem or any higher number of problems. In fact, many results have shown that the three-body problem under mutual gravitational interaction is actually chaotic. So in a sense, the solar system is actually chaotic. So one wonders, maybe tomorrow morning that we won't survive. But then there's a different question. There are longer time scales that one has to worry about. The problem does not go away if you go to quantum mechanics. In fact, it becomes much more harder. Rather than having a wave function as a function of the one particle position, what you get is a many-body wave function. For example, think of a metal. A metal is made up of electrons and ions, and you have to write down a many-body wave function which depends on the coordinates of all the electrons and all the ions. The Schrodinger equation remains the same, but the Hamiltonian becomes very complicated. So the Hamiltonian involves the kinetic energy of the ions and electrons and the ion-ion interaction, the electron-electron interaction, and the electron-ion interactions. There are barely any solvable solutions to this problem. We can formulate the problem, but we don't know how to solve it. What do we do then? Remember, this is a general problem of thinking about this idea in physics. So I just want to point out two big questions that we always ask in science, and this is the different viewpoints that comes up. One question is to ask, what's the world made of? For example, this is the description of structure. Starting from our level, we go down, there are large molecules and atoms, and if you go further, nucleons and so on and so forth. Or at the higher level, there's planets and stars and solar systems and galaxies. This is description, this is trying to find out what is where and putting them in a hierarchy. The other question is, how is the world put together? This is a very hard question in the following sense, that if I actually give you a bunch of units, say for example, there are a bunch of atoms, and I tell you the interactions between the atoms, can you tell me what happens if I put a large number of atoms together? That's an incredibly difficult question to answer. In fact, there are very, very few known solutions. This happens at every level. If you give me a bunch of nucleons, telling me the properties of the nucleus is a different problem altogether. If you give me a bunch of atoms, trying to tell me the properties of the solid is a different problem. Similar, if you know electrons and ions and trying to figure out whether a metal is conducting or not. I argue the same things must happen in a cell. If you know atoms and molecules, does not mean you know how a cell works. At a larger level, if you know how each cell moves around or how each organism moves around, does not mean you know how an ecosystem functions. If you at a much larger level, we all recognize this. Individual stars might be subjected to gravitation, but a galaxy is a much more complicated thing. It emerges from the collective many-body interactions of stars. This is a standard picture, which is it's a philosophical picture in physics. There's the reductionist approach, which is trying to find out the most elementary units that make up any physical system, and arguing that if you understand the most elementary units, you understood everything about that. The other approach is an emergent approach, which says that just because you know things at an elementary level does not mean you know things at the upper level. In fact, this was something which Phil Anderson, a Nobel laureate, put together in a very, very coherent fashion. This paper in Science in 1972 is something that everybody in science should read. It argues that, more is different. That's the title of the paper. And it argues that just because you have a bunch of interacting units, that does not guarantee for you that the emergent phenomena will be a simple output of that. These are quotes from the paper, and he makes a very strong case. The ability to reduce everything to simple fundamental laws does not mean that you can start from those laws and reconstruct the universe. That's a totally different problem altogether. And at each level of complexity, remember the complexity that I showed you earlier, there are entirely new properties appear. And the description of these new properties is as fundamental in its nature as anything else. Here's an illustration. If you think of a solid, one view would be, a solid is a collection of interacting atoms. There are valence electrons. They move around freely. There are nuclei, which are more or less static at their lattice positions. And so you try to explain the properties of the solid by thinking about the interactions between the nucleons and the nucleions and the electrons. The other approach is to say, well, I don't know, it's a black box. I'm just going to do some perturbations to it. Maybe I'm going to take a hammer and hit it. Maybe I'm going to pass electricity through it and ask it. Maybe I'll put it in a magnetic field and ask it, and I'll see how it responds. So this is like a perturbation and a response. And if I do enough number of perturbation response, I can characterize the properties of the solid. So this does not require you to understand that the solid is actually made up of electrons and ions. If you think about it for a few minutes, we developed thermodynamics in the 1800s. We developed heat engines in the 1800s. The Industrial Revolution was almost over by the 1800s. We recognized that matter is made up of atoms only in the 1900s, in the early 1900s. So even without knowing what are the fundamental constituents of matter, we were able to construct a consistent, fantastic mathematical theory called thermodynamics, which explained a significant amount of the properties of matter. This is agnostic to the fact that matter was made up of atoms. But once you recognize that, you could build a microscopic basis for that. So that's the kind of picture one is trying to build for living systems. So just because you have a large number of interacting units, these interacting units, when they come together, immediately give rise to properties that don't exist for the individual. These are attributes that exist only for many body systems and not for the individuals. Think about the following question. We all know and measure the viscosity of water. Standard undergraduate experiment, long column of some viscous liquid, put some steel ball, measure the relative velocity, and therefore you can figure out by Stokes' law the viscosity of the material. Does a single molecule of water have viscosity? Does 2 molecules have? Do 10 molecules have? Do 10,000 molecules have? I mean, how many molecules do you need before you can make a meaningful statement that there is a value for viscosity? This is really an emergent property. This does not exist for an individual molecule of water. This is a property that exists only for the collective. And so therefore, by looking at the dynamics of an individual water molecule, you cannot predict that there is something called viscosity. This is an empirical finding, and you can construct a theory at a much larger scale, which gives you a consistent picture. A more dramatic thing that happens when you have collective states of interacting units is the phases of matter, something that we learn in school. That there are phases like the solid, liquid, and gases, but then more sophisticated ones will learn some more phases. There are phases like plasma, Bose-Einstein condensates, blackbody radiation, BEC, and so on and so forth. What we learn is that there are ways to control the phase of matter by playing around with certain emergent macroscopic properties. You don't control the individual interactions between the units when you want to, let's say, heat a bowl of water. What you do is to just change the temperature. Temperature is not a property of an individual unit, it's a property of the collective. And so we recognize this, and therefore we developed ideas of phase diagrams. So if you have a pressure and temperature phase diagram, we know that you can increase the temperature and go from something that looks like a solid to a liquid to a vapor phase. We also recognize that there is differences in the way the fundamental units are organized in space and time in these units. In a crystal, there's periodic, regular arrangements of the fundamental units, be it atoms or molecules. In a liquid, the order is not as good as the solid, but there is still short-ranged order. In a vapor, on the other hand, there's hardly any order. It's more or less an isolated system. It's more or less a system of independent molecules. So this connection between microscopic structure and emergent macroscopic properties is what we learn in thermodynamics. Right? So we build a emergent description, we build a coarse-grained description. We say that we can ask for other quantities which will tell you the stability of matter at that level. For instance, if you have a bottle of water, you leave it undisturbed for a long period of time, and you look at a subsystem, a small volume inside that water. We know the following, that the properties of that subsystem is governed by thermodynamics. In particular, there's the free energy, which is a combination of the internal energy, entropy, and so on, depending on the kind of boundary conditions you have. And we recognize that the equilibrium state, that is the state that the system is in after a long period of time, is one that minimizes free energy. And so therefore, if you change the temperature, the pressure, the chemical potential, and so on, you can actually change the state which has a minimum free energy. And these changes can sometimes be abrupt, and those changes are the phase transformations. We have a theory, a microscopic theory for understanding thermodynamics, only for equilibrium thermodynamics, and that's called statistical mechanics. Again, something that we teach in our undergraduate education, where we compute the partition function, and from the partition function, we build the thermodynamics of macroscopic systems. Thermodynamics also gives you a way to think about the emergent behavior of large aggregates of matter. For instance, a solid is defined as something which has a non-zero shear rigidity, in the sense that if you take a solid and you shear it and you remove the shear, well, the solid will snap back to its original position. So it has a shear rigidity. It resists any applied shear. We understand this by saying that for small shears, the stress and the strain are linearly proportional to each other, and the slope or the proportionality constant is what we call the elastic modulus. It could be the Young's modulus, the bulk modulus, or the shear modulus. On the other hand, for a liquid, if you shear it, it moves. But if you remove the shear, well, the liquid does not go back to its original position. The new position is as good as it is. On the other hand, the liquid actually responds not to a strain, but to a strain rate, the speed with which you are deforming the material. And we realize from empirical evidence that there is a linear relationship, at least for small strain rates, between the stress and the strain rate, and the proportionality constant is what we call viscosity. Remember, at this macroscopic empirical description, you're measuring a coarse-grained quantity like a stress or a strain rate, and the proportionality is the viscosity. This is an operational definition of a material parameter, and not something that you figure out by looking at the properties of the individual atoms. There are objects which are intermediate. All our everyday stuff, think about toothpaste, food, our own tissues. These are neither solid nor liquid. On short time scales, many of these behave like a solid. They respond to elastic stresses and jump back to their original position. Wait long enough, they can flow like a fluid. So there are ways to understand mathematically these kinds of materials. These are viscoelastic materials. Could be a viscoelastic solid or a viscoelastic fluid. Inherent to all these pictures was the idea of coarse-grained. So here's an example. If I have a solution, I put in a glass of water some amount of a colloid and I get a suspension, I can think of it at various levels. At the very fundamental level, I could think about maybe water molecules and some charged objects sitting there. Maybe I can think of this like a hydrophilic medium. I do not look at the individual water molecules, but I think about the colloids, and maybe that's a diffusive dynamics, Brownian motion. Much larger scale, this is basically something that has a viscosity and it flows. Perhaps you can coarse-grain that even further and think about lattice solutions. Implicitly, we have this idea in our head whenever we write simple descriptions of matter. For instance, when you think about the continuity equation, the density, the mass density rho, is not of that of an individual unit. If this is the picture of a bunch of individual units, you coarse grain. You look at small volumes, count the number of molecules there, divide by the volume, and that gives you the coarse grain description of a mass density. The mass density is a smooth field, and it's for that smooth field that you write equations of continuity. Going up, you write equations for Navier-Stokes fluids. All problems of fluid flow in pipes and atmospheric flows and geophysical flows start with the Navier-Stokes equation. You don't start with atoms. That's not useful. In fact, it might come as a surprise to many of us that even Maxwell equations are actually not microscopic. They are really macroscopic coarse grain descriptions. They're at the same level as the Navier-Stokes equations. The book by Griffiths, Introduction to Electrodynamics, in the 4th chapter, he actually makes a very nice statement. The Maxwell equations, the electric and magnetic fields for which you write the Maxwell equations, are really for electric and magnetic fields which are coarse-grained over many thousands of atom units. At the level of the individual units, the fields fluctuate very, very widely. It's only when you coarse-grain them that you get these smooth descriptions and macroscopic electrodynamics emerges. So coarse-graining is something which is inbuilt, and that's the view that I want to take. Rather than thinking about individual proteins and individual genes or even individual cells, if I'm looking at the tissue level, I want to ask collective dynamics of interacting units. The interacting units could be molecules at the cellular level or could be whole cells at the level of the tissues. The kind of variables that one wants to write are things like density fields, deformation fields, flow velocity fields, perhaps orientation fields, perhaps also include chemistry, the fact that different molecules can convert into one another. The kind of material properties that one will necessarily have to put in here are things like diffusivities, turnover rates, friction, elasticity, viscosity, adhesion, contractility, and so on. Okay, and one asks if there are regularities in the spatiotemporal variations of these quantities. And these are the emergent morphogenetic patterns. Here are 2 books which try to emphasize this viewpoint on biology. One book by D.R.C. Thompson, which I'll come back to in a few slides, is something which laid the fundamental thinking about these processes more than 100 years ago. A more recent book by Forgax and Newman talks about the biological physics of developing embryo. This is about 20 years old book, one of the very first books which talked about development from a physics perspective. Here's the big picture. Even if you don't know the biology, you would have heard this in school. Even in living systems, there are these structures called genes and proteins and cells and tissues. So there are these fundamental things called the genes, and the genes somehow interact with each other. The genes via transcription and translation make proteins. The proteins do the job of assembling the cells and tissues. The cells interact to form tissues. Tissues interact to form organs. Organs interact to form organisms. There's this hierarchy of descriptions that you learn in biology. There's a similar hierarchy in physics. We learn that if you give me a bunch of fundamental units, maybe atoms, maybe molecules, and you tell me the interactions between them, you put a large number of such interacting units together. At least for equilibrium systems, there's a formalism called statistical mechanics, which tells you what are the emergent properties. In fact, we know it to such a good extent at equilibrium that we've been able to build things that don't exist naturally, metro trains, for instance. The relevant variables where we use to describe such systems are not molecular properties. These are things like pressures, temperature, magnetic field, free energies, entropies, and so on. This should strike you. In biology, there are genes, there are proteins, and then there are giraffes or creatures like us. What's the thing that tells you how to go from the interactions between genes and proteins to organisms? In other words, what's the analog of statistical mechanics and thermodynamics of living systems? So that's essentially broadly the picture of physics of life. That we've discovered DNA, we've discovered proteins, we understand how genes go to proteins to some extent, but then we don't understand how they make a cell or how cells come together to form tissues and organs and organisms, let alone ecosystems at a much larger level. So there's some really fascinating physics which is missing here. Rather than being qualitative, we want to make it quantitative. We want to make it like we do in usual physics, theory, experiment, interaction, and build the statistical thermodynamics of living systems. One thing that you immediately recognize as soon as you go to living systems is that they are out of thermodynamic equilibrium. Remember, when we teach thermodynamics to undergraduate students, we emphasize that a system is in thermodynamic equilibrium if it's in thermal equilibrium, if it's in mechanical equilibrium, and if it's in chemical equilibrium. In other words, the temperatures of different parts of the system must be the same, the pressure must be the same everywhere, and the chemical potentials must be the same everywhere. If not, the system will relax until it reaches a thermodynamic equilibrium. Once it's in thermodynamic equilibrium, we have a formalism. Thermodynamics, the microscopic basis being equilibrium statistical mechanics, and we have a way of predicting even the large-scale phases of matter. The complexity will increase if you have more and more components, and so therefore the interactions become more complicated. But at least in principle, there is no problem. If you have a system which is not in equilibrium, we have even an in-principle problem. We do not have a generic non-equilibrium thermodynamics so far. What we have is many rules of thumb, empirical ideas, things that work in a few systems, a generic idea which can capture any non-equilibrium system. We do not have it in physics. In equilibrium thermodynamics, in equilibrium statistical mechanics, we learn if you know e to the minus beta h, you're done. Everything at equilibrium is done. There is no such universal thing for a driven non-equilibrium system. So one wonders, should one even go to living systems? Well, let's turn the argument around. Maybe we will actually build non-equilibrium thermodynamics by looking at living systems. In fact, they are the most prominent example of non-equilibrium systems. Like I argued earlier, there are systems which are out of equilibrium for the very reason that we eat food. If you don't eat food, like Schrodinger said, you don't consume negative entropy, and so you wait long enough, you will actually reach thermodynamic equilibrium. In other words, you'll be dead. Death is thermodynamic equilibrium. Being alive is being away from thermodynamic equilibrium. So you would like to understand how is it that you maintain a system out of thermodynamic equilibrium. Living systems use this idea of non-equilibrium to self-organize. I want to show you a bunch of examples of self-organization, and then I'll come back to thinking about the problems that I look at. Broadly, in the present state in biological physics, there are physical approaches, both theoretical and experimental, to broadly these classes of problems. There are problems at the cell and developmental level. There are problems at the neurobiology level. The brain, each one of us is using this to argue these points, is itself a condensed matter system, is itself a system where there are plenty of neuronal signals going through, and we are analyzing that. It's one of the probably the most strongly correlated system that we know of so far. The third is trying to look at ecological systems and trying to understand how they evolve on much longer timescales. I focus on cell and developmental aspects. I try to understand self-organization processes at the level of cells and tissues and organs, and try to bring out non-equilibrium active physics there. This book that I referred to at the early couple of slides ago is actually a pioneering book. It was first published in 1917, Growth and Form by D.R.C. Wentworth Thompson. And probably one of the first books that really argued for the fact that the shape and form of living systems will necessarily emerge from physical laws. Here's a quote where he actually says that, cell and tissue, shell and bone, leaf and flower are so many portions of matter, and they have to be in obedience to the laws of physics. And it's these laws of physics that will make them move, mold them, and conform them. But what are the correct emergent descriptions of physics appropriate to the living systems? Well, then you see the time, it's 1917, and at that point of time, quantum mechanics came up, and all physicists ran off to do quantum mechanics, and everybody forgot biological physics. So it took some time, about half a century later, when people started, all the solvable problems in quantum mechanics were solved, and all the hard problems were left. Now people started looking at other problems. People came back to thinking about living systems as physical systems. That's when the revival again starts by people like Schrodinger, Max Delbruck, and so on. Let's list out some of the unique features of living matter and contrast it with non-living matter. First thing is complexity. If you haven't seen this, it's a surprise. This is actually one of the possibly the simplest living creatures that we know of. It's a bacteria. It's E. coli bacteria. It lives in all places. In particular, it's there in right now in every one of our stomachs. It aids digestion, several nice variants of it. It's just a capsule. If you think about like a tablet that we all consume, about 2 microns in length and about 1 micron in width. There are these long appendages called flagella which allow it to swim. So I will go in and zoom into this. These beautiful pictures are taken from this wonderful book, The Machinery of Life by David Goodsell. If you zoom in to this, you start seeing emergent levels of complexity. So we are zooming into this region where there's a flagella appended here. You see a motor-like structure sitting there. This is a nanomotor. You see a long yellow wire that's floating around. That's actually DNA. These large globules that you see are a huge number of proteins. Some of them are histones, some of them are ribosomes. There are plenty of structures sitting there. I won't bore you with the details. So if you zoom in further, you start seeing structure at every level. There's some DNA which is being transcribed into mRNA. The mRNA is being eaten up by the ribosome and translated to proteins. If you zoom in further, you'll see familiar structures. Can you see these tiny, tiny triangle-shaped objects? Those are water molecules. So you see the dense packing of molecules that happens in a living system, the variety of structures that are there, the complexity of structures that are there. And it's amazing to think that anything even could happen here. One would think maybe that, everything will become randomized and so therefore nothing systematic should happen. That's not true. This tiny creature shows directed movement. It can actually move its flagella in response to food and go towards regions of food, go away from regions of poisons. So it has a sense of which way to move. How does it break directional symmetry? How does it even decide which way to turn its axis? These are problems which have troubled physicists for a long time. We have a reasonable understanding of these things. There are many, many problems that are still open. Perhaps the more important thing, it makes copies of itself. That's something a piece of inanimate matter can never do. We all have mobile phones. How nice it would be if the mobile phone made a copy of itself. It'd be superb, right? I mean, make a baby of the mobile phone and have mobile phones upon mobile phone. That never happens. Even though mobile phones are so complicated structures, replication spontaneously never happens. Living systems do that in and out every day. This is a puzzle. I mean, this never happens. However, a cell, all you need to give is some directed, undirected energy, easily makes a copy of itself. In fact, all of us, the cells in our body more or less turn over in a day's time scales. The cells that you had yesterday are not the same cells that are there in your body today. And so therefore, there is a turning over of material, yet our form and structure remains the same. At a larger level, replication is not always identical. Many a times there are errors, mutations that can happen. And these mutations can be selected by the environment. And this is how evolution happens. A way to think about evolution is to organize them into phylogenetic maps, like the one that's shown here. A significant number of organisms that we know of in our familiar everyday life are a very, very small part of this evolutionary tree. The majority is actually occupied by bacteria, the tiniest creatures that I showed you a few slides ago. Even those tiniest creatures have these fantastic ways of organizing things. How is it that they do? Something that bothers me a lot. Multicellular life. We all are an example of multicellular life. Once upon a time, we were a single cell in our mother's womb. That single cell split into 2, 4, 8, 16, and so on. The cell started reorganizing and our form and shape was born. This happens across many creatures. So here's a movie which shows the development of a zebrafish. A tiny fish, you see a picture of that at the bottom right. The movie starts by a few cells, I think about 4 to 8 cells. the cells divide, they start moving around. At some point of time, you start seeing some fascinating familiar structures. The fish is a vertebrate, so therefore you see the backbone coming up here. This is the same somites that all of us have. An eye-like structure starts forming over here. At some point of time, you'll also see pigmentation patterns coming up. Remember, this is just a few millimeters, hardly a millimeter in size, and this is real time. These days, microscopes, the tools provided by physics, are so powerful that we can record these processes in real time. We have plenty of data. We can track almost every molecule by fluorescence techniques. We can follow that in space and time. We can get fields of deformation. We can get fields of geometry changes. It sort of begs for a theoretical physics. We see this, but why is this happening? What are the simple physical laws that are sitting here? All of us would agree that, there must be physical laws. But what are those laws? That's the kind of question that we are really interested in. Can we assemble living matter? It turns out no. If you break up your mobile phone, we can take it to the repair person and he can reconstitute that. We can never do that for living matter. So here's a nice experiment from this book by Alfred Weiss. He says, let's say you take a 6-day-old chick embryo. It's not a fully formed chicken yet. And he says, just crush it. Don't remove anything, don't add anything, just crush it. And it forms a homogeneous mixture, centrifugated. The heavier ones will be at the bottom, the lighter ones will be at the top. This is ordered in some sense. This is disordered. But this is also ordered, but in a different sense. It's something very peculiar. The chemical composition is identical, yet it's easy to go one way, almost impossible to go the other way. So it's in a way the organization of living system that's happening, the way they self-organize, that makes living things different. So here are some of the unique features. They're very complex, they replicate, they self-organize, they evolve and adapt. I showed this, so let me skip these 2 slides. Okay. The kind of problems that I'm really interested in are problems in which multicellular creatures develop. Here's a frog embryo to compare with again. Again, you see a similar process by which the initial cell divides into multiple cells, form emerges, the inside, the outside of the cell of the organism forms, and at the end of the day, you have something that has, it was just 1 micron cube bag of chemicals, and 1 day later, a tadpole comes up. We all recognize that 1 micron bag of chemicals was not alive, but the tadpole is alive. What is it that makes them alive? Okay, how am I doing for time?
Yeah, another 10 minutes you can take, no problem.
I'm done, then I'm fine. The kind of problems that really interest me are problems, where morphogenesis happens. How do shape organs, how does shape emerge? How does segmentation emerge? In other words, how do creatures decide what is the head direction, tail direction, front, back, left, right? These are problems of symmetry breaking. So here's an example. Fruit fly, Drosophila, if you keep banana in our homes, there's this tiny black insect that comes up there. It's a standard creature to study development. Very early patterns that come up in this creature lay out the body plans. And these are problems where people have studied pattern formation of molecules and try to explain quantitatively how the creature actually forms these kinds of shapes. Let me skip these slides. I just want to tell you that these are not, qualitative descriptions. In the fly, we've been able to measure quantitatively molecular concentrations of certain chemicals, write down physical descriptions, compare experimental values with theoretical predictions. They work. So in a sense, it starts giving you plenty of confidence that a physical description of living systems is indeed possible, given that you do quantitative measurements. Yes, the physics gets more and more complicated, but it's still physics. A father of these kinds of ideas is Turing, the same Turing of the Turing machine, Turing. He speculated sometime in the 50s and 60s, that simple diffusion, Brownian motion, coupled with chemistry, can actually lead to the emergence of spontaneous patterns. His ideas were forgotten for many, many years. Sometime in the early 90s and early 2000s, people actually showed that such Turing patterns underlie even our digitation. The fact that we have 5 fingers, even mammalian digitation patterns, is really because of Turing patterns. One aspect that's really missing in Turing systems is the idea of forces and fluctuations and so on. In the interest of time, let me skip that and I'll just go to active materials. The novel framework that's been developed in the past 2 decades is this framework of active matter. We all recognize that cells and tissues are driven out of equilibrium. The process is metabolism. In other words, there's always an energy flux into the system. A framework to develop the thermodynamic descriptions for such systems is what's called active hydrodynamics. This is a formalism that couples chemical reactions with deformations, flows, orientations, and so on. It's been extremely successful in trying to explain intracellular properties, large-scale tissue-like deformations. For example, this is the wing disc of the fly, or at a much, much larger scale, even birds, flocks of birds and schools of fish and swarms of insects. The kind of questions that one asks are thermodynamic, not about the individuals, but more about the collective dynamics. In my own research, I look at this particular structure called the cytoskeleton, which is really a structure that is responsible for the movement, polarization, and division of cells. And I use frameworks of active matter to try to explain quantitatively, by collaborating with experimentalists, how these processes go through. I don't want to, make a big deal of the equations, but I just want to tell you that just like fluid mechanics, elasticity, thermodynamics, there is very consistent mathematical frameworks for understanding this, so much so that it can actually make very quantitative predictions. The last part is going into my research, where I try to look at the properties of such systems to such an extent that one can actually measure experimentally fluid flows inside cells, write down mathematical equations, compare the predictions of mathematical equations with experimental measurements, and they seem to work. It's completely okay if the equations were fast and you did not get it. All I want to show you is the framework that I was saying about theory, experiment, comparison to work in living systems at the cellular level. To extent that we've actually, in the recent years, been able to explain cell polarity, the process by which a cell polarizes, one end of the cell becomes different from the other end of the cell, by large-scale flows, can write down a thermodynamic theory, and the theory matches experiment extremely well. We're working on a bunch of problems. We try to think about how shape comes up. For instance, cell division is a classic example. And these interface between active patterns and dynamical shape leading to cell division patterns is something that many of my students work on. Our idea is to understand that if you look at unpatterned, unshaped materials, how do they acquire shape? How do they get a head and a tail and a fin and a limb and so on? One recent movie, and I will conclude, we've been able to explain cell division, the fact that a single mother cell spontaneously divides into 2 daughter cells, and with increased strength of activity, how asymmetries come up in a very quantitative fashion in recent years. So here's a summary. The kind of problems that I look at are problems where there are active stresses. I write down hydrodynamic descriptions. I quantitatively compare theory with experimental data. I look at how shape, size, geometry, pattern come up. We are nowhere near explaining the phenomena of living systems. It's a start. We start now. Perhaps in a couple of decades, we'll be able to do some justice to that. So I'll conclude. Here's a summary. As far as we understand, living matter is soft in the sense that quantum mechanical effects don't seem to play too much of a role. It's active, it's non-equilibrium, it's very complex, and it evolves. The physics of living systems is actually in a very nascent stage. It is amenable to physical descriptions, and there's new and emergent physics lurking there. It's highly interdisciplinary. You need to know significant amount of physics, significant amount of mathematics, computation, and of course biology to be able to make some progress in this field. But that's also the challenge. It presents some of the hardest problems in physics and mathematics. So here's a cartoon that appeared in the New York Times some years ago. So this was a cartoon that somebody wrote to say which areas of physics are hard. Newton's laws are easiest. Special relativity becomes harder. Quantum mechanics and general relativity becomes even harder. But sand, the physics of sand is incredibly difficult, far difficult than general relativity. And I make a claim that living matter is off the scale. But there is promise. And to start that promise, this is an effort. We have started a new PhD program in TIFR across the TIFR system called, surprise, surprise, Physics of Life. We are targeting very exceptional and very creative and adventurous students who have strong foundations in physics, mathematics, computer science, not biology, but physics, math, computer science. But they want to work in cutting edge theory and experiment problems in biology. We have a coursework which will train people to look at these advanced ideas. We have joint projects between many of the TIFR centers. It's a very special stream, plenty of flexibilities at this level, something we are very, very proud of. We've been doing this for the past 3 years now. It took many years of effort to convince people to start this PhD program. It's become nice. We already have 3 batches of students. And in a couple of years, we'll have a first set of students who will have PhDs in this new area called Physics of Life. Here's a set of books that one could refer to. The top row shows some semi-popular books. The Many Phases of Matter by G. Venkataraman is something I strongly recommend. It goes all the way to more recent books which try to argue for a physical description of living systems. But the ones at the top are more semi-popular. There are also standard textbooks at the BSc, MSc level, where one starts looking at physical descriptions of living systems. The bottom row, again, goes up in increasing order of difficulty, starting from, say, at the undergraduate level to master PhD levels. I will stop there. I can do all this research because, TIFR funds me, Department of Biotechnology funds me, the Max Planck Partner Group and the John Templeton Foundation have given me funds. And I have a wonderful set of students who, are as crazy as me to come and work on these kinds of problems. Thank you. I'll stop there.
Thank you very much for a very exciting talk. Now there is time for some questions and answers. If anybody would like to ask any question, they may do so. One by one, please. To start with, I would like to know, is there any such thing as the simplest unit of life? Just as we have atoms, what is the simplest, modest unit of life?
Probably bacteria. There doesn't seem to be anything simpler than that. In fact, that's one of the reasons why I showed that picture. What we could think of possibly as the simplest unit of life is itself so complicated.
Yes.
So therefore, we are quite far in understanding and understanding those physics.
Going to Umesh, Professor Umesh. Please ask Professor Umesh.
One second, sir. I was facing difficulty in unmuting.
Okay.
Fascinating lecture.
Thank you.
What is there some theoretical basis for tissue engineering, which is going on?
Very much so. One is to understand how to sculpt tissues and see how to engineer tissues, for example, when you have wounds and things like that. One level could be at a empirical level, much like medical things that we understand. Our work tries to understand the fundamental basic aspects.
Right.
How does the tissue, decide when to deform, where to deform, and things like that.
Right.
We understand basic properties. We are nowhere near a level where we can understand the engineering tissues to a certain level. Right now, it's more empirical. and not driven from physics-based approaches. Some decades, it will take some time.
So in tissue engineering, do they kind of fabricate tissues of only one kind?
No. Several kinds, right? There are many examples. It could be probably one is thinking about human level, but then one can think about tissues at even other organisms, right? There's a creature called Hydra, which is a small creature, lives in water. It's small enough and not so complex that we can understand the biology very well. It makes tissues of its own. It makes, limbs and heads and tails. And that physics we've been encountering and really understanding that from the past decade, to a certain extent that we can actually engineer things there. Maybe some of the ideas that we learn there could be useful to human tissue further down the line.
Right.
Human tissue is far more complex, and we don't know.
Yeah. Thank you.
What are the factors that drive a living organism towards negative entropy states? What are the factors
To drive towards
driving a living organism toward negative entropy state? What factors? What are the causes? Have they been identified?
So essentially, it's metabolism. It's essentially energy flux, right? So we learn that if you have an isolated system, the entropy will increase.
Yes.
But if the system is not isolated and you are actually providing energy into the system, then what? Well, then there's no such rule called the entropy should increase. Entropy could also decrease, but that's negative entropy, right? Yes. Entropy going down is like negative entropy. Yes. Kitchen experiment, we put water in a jar and you heat it. Well, that's not an equilibrium system because you're constantly supplying energy to the system. The way you're doing it is by heating. The way living systems have developed how to counteract the effects of increasing entropy is to take in high energy molecules. The food that we eat, at the end of the day, various processes of metabolism, glycolysis, Krebs cycle, and so on, generates a set of molecules which are high energy molecules. The hydrolysis of these high energy molecules, like an exothermic process, generates energy. And so if you generate energy, surely you can reduce entropy. And so therefore, Schrodinger's book actually makes a very nice case. We all learn in school why we eat. He says we all learn to get energy. No, to actually get negative entropy. That's the essential reason why we eat.
I want to ask that in the expression free energy, you have used mu n.
Correct.
What that stands for mu n?
Yeah, mu is chemical potential and n is the number of atoms. So let me go back to that.
You have used, of course, the continuity equation, momentum, that is Navier-Stokes equation.
That's correct.
And you don't go for the energy equation?
We can. I didn't show you that. That's all. Of course, you have to worry about that too.
So you are using even the energy equation also. And combining that Navier-Stokes equation and the energy equation?
Yes.
And the equations are to be coupled and solved for getting the solution?
Yes, they're very highly coupled, very highly nonlinear. So analytical solutions are almost impossible. Most of the time, we do it numerically.
Very good. You are actually making use of mathematics, physics in living systems.
That's the whole idea.
The objective, Professor KS. Professor KS, you can unmute and ask your question.
KSS.
Hello, sir. Thank you.